tritium capacitance field established by beta-decaying nuclear masses can be influenced by the field of an external capacitor. If that capacitor field is strong enough in voltage, the beta-decaying tritium capacitance field can be completely absorbed into the external capacitor's field. This absorption captures the beta-decaying energy and prevents the decay. This beta capture in a capacitor field results in a power gain. Our data indicates that for every 3.67 grams of beta-decaying thorium captured by a capacitor field, there will be 1 megawatt of continuous power output. 3.67 grams of thorium-233 captured is equal to a megawatt of new energy in the form of electric current. To recognize how this is possible, it will require understanding how the tritium and external capacitor fields interact with one another and within the mathematics governing capacitance, voltage, and electrical charge.
In electronics, charge is defined as the current flow in amperage, or the number of electrons per second, which are discharged in 1 second of time. 1 coulomb of charge is defined as 6.24 billion electrons discharged over 1 second of time. A coulomb of charge is therefore equal to an electron discharge frequency of 6.24 billion Hertz. Charge is the exact equivalent of electron discharge frequency. The whole of a radioactive mass can have a common charge. This charge is the frequency of Betty electron discharges. The whole of the radioactive mass undergoing Betty decay can only have this common charge if the individual Betty decaying atoms are components of a single capacitor-like field. The common capacitor-like field can be established for the whole of the radioactive mass by the multiplication of the capacitor-like fields of the individual tritium nuclear elements contained within the mass. Our data has proved that the common capacitor-like field of a B2 decaying mass can be intensified if the radioactive material is integrated into the negative pole of a capacitor. Mathematically, this increase must be by the square of the influence factor. This proves that the capacitor-like field of the radioactive mass is being multiplied by the field of the external capacitor. We will show that this multiplication of fields can produce a field strength which has never before been observed. A squared factor multiplying the radioactive mass's capacitor-like field provides that the frequency of discharge is increased by the same factor, while the electron voltage of B2 discharges simultaneously decreased. As our external capacitor field is increasing the frequency of B2 discharges, it is simultaneously decreasing the electron voltage of those discharges.
Because the field of the external capacitor multiplies the tritium capacitance field of the radioactive material, the frequency of beta discharges must be increased to compensate for the intensified tritium field. If the energy stored in that capacitance field remains constant, as it must with beta decay, then the voltage of discharge must also be decreased in direct proportion to the increase in the frequency of discharge. This follows the standard formula for charge, voltage, and energy. Our experiments have proved that beta frequency increases are directly related to the amount of voltage applied to the external capacitor. For the test series displayed on your screen, a 60-volt capacitor increased beta frequency to 122% of no field, while a 220-volt capacitor increased beta frequency to 172%. All of these results are compatible with other test series. The 122% increase for the 60-volt is fairly low and not typical of other series which tended to approach 130%. This series, with its lower 60-volt increase, illustrates that the greatest variance found between series always occurred for the lowest voltage. As the voltage increased, the change in beta frequencies tended to stabilize when test series are compared. Although the external capacitor can alter beta frequency, it cannot really alter the energy behind beta decay. It can only alter the way that the constant beta energy is distributed between the frequency or charge and the electron voltage of beta decay. But what happens when the external capacitor field suppresses beta electron voltage to something lower than the voltage needed to dislodge the electron from the neutron and to convert it to a proton? In that case, the decay will cease and the tritium neutron will no longer be converted to a proton. The tritium nuclear element will be captured or retained in its parent elemental form while it undergoes a continuous series of failed attempts at decay. This is the source of the nuclear power extraction which external capacitors promise. From the quantum dimensional model of the neutron, we know the exact electron voltage which is needed to dislodge the electron from the neutron. When the frequency of beta decay is increased to 250% of the no field, the electron voltage is reduced to 40% of its original. Electron voltages below this 40% will no longer convert the neutron to a proton. We know this to be true both mathematically and experimentally.
The energy invested during B2 decay comes from the conversion of the neutron to a proton. It is an acknowledged fact in atomic physics that the neutron is composed by the fusion of an electron with its negative charge and a proton with its positive charge into a single neutron mass, which is known to be neutral with respect to the influence of magnetic fields. B2 decay occurs when the fused electron is dislodged from the neutron, converting the neutron back to a proton. It is also an acknowledged fact of atomic physics that the fusion of the electron with the proton to make a neutron is accompanied by an increase in the mass of the electron. During the fusion process, the electron has acquired 2.5 times its mass. The mass of the neutron is equal to the mass of the proton plus 2.5 times the mass of the embedded electron. The mass of the neutron is 1.6749 to the minus 27th power kilograms. This is equal to the mass of the proton at 1.6726 to the minus 27th power kilograms plus 2.5 times the mass of the electron, taken to 4 places to the right of the decimal point. During electron-proton fusion, the electron has increased its mass by 2.5 times. Conversely, the electron being dislodged from the neutron during B2 decay must lose some of this excess mass. While consensus science does not know how or why the electron increases in mass while inside the neutron, they are aware that the conversion of this excess mass during B2 decay controls the energy released. The reference materials for nuclear engineering recognize the energy released by B2 decay as approximately 766.5 thousand electron volts. Using Einstein's equation for the conversion of mass to energy, this energy of beta release represents the increased electron mass in the neutron converted to energy. In order for the electron to remove and encapsulate the proton's positive charge in 4-dimensional space, the electron's mass must be increased 2.5 times by quantum force. To remove the positive charge from the proton and encapsulate it, the mass of the electron must be increased 2.5 times. The electron is a quantum particle and not rigidly structured as is the proton. In part 1 of this video, we identified that quantum force is the force of reserve time. We are here adopting the Newtonian, rather than the Einsteinian view of time. Newton introduced his laws of motion with the following description of time. Absolute, true and mathematical time, in and of itself, and of its own nature, without reference to anything external, flows uniformly. Time is a force which flows without reference to anything external, and therefore can force the electron into greater mass without any restriction. Albert Einstein's 1905 equation for the dislodging of an electron from an atom explained the photoelectric effect. 20 years later, Einstein received the Nobel Prize for his formula, after it had been experimentally proved accurate by Robert Millikan. Einstein's formula also has application to the dislodging of the electron from a neutron during B2 decay. His formula proposes that not all the energy applied to an atom is released with the electron when it is ejected. A portion of the total energy applied performs what Einstein called the work function. That portion is applied to the dislodging of the electron, and the remaining portion is the amount of energy discharged when the electron is released. Discharge energy equals total energy minus the work function energy. We know the total energy which can be applied to the neutron to dislodge the electron during B2 decay. We also know from nuclear engineering the amount of energy released during B2 decay. From these figures we can calculate Einstein's work function, or the amount of energy which must be expended to dislodge the electron from the neutron during conversion. The total energy is the energy potential of the embedded electron from conversion of its mass to energy. This calculates to 1,277.498 thousand electron volts. From nuclear engineering tables, we know that the energy released during B2 decay is 766.499 thousand electron volts. Total energy minus discharge energy equals work function energy. Work function energy is 510.999 thousand electron volts. We also know that the electron volts of the tritium capacitor-like field must be the total energy electron voltage of B2 decay. We know this because, if the electron volts of the capacitor-like field were only the B2 discharge electron volts of 766.499 thousand electron volts, then the external capacitor could not affect the frequency of B2 decay. If the external capacitor were only influencing a partial of total B2 decay energy, as it would if the tritium field voltage were only discharge volts, then the rate of discharge could not be changed. The tritium field voltage must be total energy volts. It is only total energy volts which can be reduced to the decay threshold voltage of 510.999 thousand electron volts with the resultant complete suppression of B2 decay. The complete suppression of B2 decay will occur when the external capacitor X factor reaches 2.5. Dividing total energy electron voltage by 2.5 remained as the required work function of 510.999 thousand electron volts needed to remove the electron from the neutron. Voltage below this threshold will not be able to remove the electron and B2 decay will be suppressed. We know this, not only for theoretical and mathematical reasons, but because our experimental data proved it to be true. The high-voltage capacitor experiments proved that B2 decay was suppressed when the capacitor's X factor was greater than 2.5 as measured by increases in B2 discharge frequencies. It is these high-voltage capacitor experiments which proved that B2 decay can be integrated into the external capacitor field to generate a current of significant increase in power. It is to that experiment which we must now turn.
Beta decay is a known but little understood form of radioactive decay which has never been successfully applied to the generation of nuclear energy. That is, has never been successfully applied until now. The quantum dimensional model of the atom has suggested a series of experiments which proved that beta decay can produce a cleaner and safer form of nuclear energy than is provided by standard fission reactors.
The high-voltage nuclear capacitor is of a different design than the low-voltage capacitors which produced the data previously reported. The low-voltage capacitor uses a standard dielectric separator between plates, a 1/4 inch of perforated polyethylene, was used as the dielectric separator. No such dielectric separator is used with the high-voltage capacitor. The high-voltage capacitor is designed to operate with thousands of volts, and only the distance of separation between the plates prevents sparking. A dielectric separator would also prevent the streaming of beta electrons from the radioactive material in the negative plate towards the positive plate. In some respects, the high-voltage nuclear capacitor must operate like a beta-streaming cathode tube. A high-voltage nuclear capacitor design was used to test the beta emissions of thorium-234. Thorium-234 is the beta-decaying byproduct of uranium ore. The beta emission were very low level. This was a requirement of the research design, because individual beta events had to be separate and countable. For the high-voltage capacitor tests, gamma emissions associated with beta decay were used to indicate changes in decay rates. This was necessary because the beta electrons themselves were possibly being absorbed into the capacitor circuit and no longer available to the detection equipment. This use of gamma alone as an index for beta decay activity proved to be extremely accurate, as analysis of the data will shortly prove. Under appropriate high voltage for the external capacitor, the record of the distribution and rate of beta events with no field present becomes this under a field. We cannot really tell what we are hearing nor why it shows that the thorium-234 has been captured, unless we look at the fine structure of the data record. The fine structure data record demonstrates that the high voltage field has induced thorium-234 to emit two different species of beta emissions. It can be seen by the fine structure record that some of the increased discharges are beta discharges, but some of them are only ionic discharges similar to those which produce the electron stream in a cathode tube. We know that these discharges are ionic because the detection device identified the electron voltage of the discharges as equal to that of the field voltage of the capacitor. The discharges are being replaced from the negative plate of the capacitor as they stream towards the positive plate. We know they have composed an electron stream because they are generating an electrostatic field similar to that produced by cathode tubes. The ionic discharges are sub-gamma and in the lower limit of the Geiger counter's detection range. They can be heard fading out of the recording in a wave-like pattern. They disappear to hearing detection, leaving only the beta emissions. Whether audible or not, however, the recording device faithfully records their presence. The data record gives strong evidence that the thorium-234 has been captured. The rate at which the high voltage field increases beta discharges shows that the electron voltage has fallen below the level required for decay to occur. Beta discharges, excluding ionic discharges, are 267% of the discharges under no field. The external capacitor's X factor is defined as the percentage which the field increases discharge frequency. The X factor is determined by dividing the field-induced emission rate by the no-field emission rate. The X factor for the beta discharges is 2.67. The electron voltage is being simultaneously reduced by this X factor. The total electron voltage for beta decay is 1277.50 thousand electron volts. Dividing this number by 2.67 remained as 478.46 thousand electron volts. This is below the threshold electron voltage required to dislodge the electron from the neutron and convert it to a proton. That threshold is 510.999 thousand electron volts. There is a second line of strong evidence for the fact that B2 decay has been suppressed and thorium-234 captured. The B2 discharges have acquired a Fermi resonance. A Fermi resonance is a known pattern to the discharges of connected oscillators which occurs on the atomic level. It is a quantum pattern in which 1 quanta of energy is exchanged for 2 quanta of energy in sequential discharges. A Fermi resonance could not occur unless the thorium-234 atoms are retained under tension as permanent oscillators. It could not occur unless B2 decay had been suppressed. The high-voltage nuclear capacitor has first suppressed the tritium capacitance field to below the B2 decay threshold. Then, influencing much less energetic ionic discharges, it has forced the tritium electron voltage to an equivalence with itself, and integrated the nuclear field with its own, producing a cathode electron stream of the tritium discharges. This is accompanied by a power gain of 3.42 times. The wattage output to the positive terminal by the electron stream is an estimated 3.42 times the wattage input to the negative terminal by the external capacitor. We know this to be true because the operating high-voltage nuclear capacitor has acquired an electrostatic field typical of those produced by electron streams, but a field of much greater intensity than has ever before been observed.
One of the unanticipated results of our experiment controlling beta decay using this external capacitance field was that we were projecting a strong capacitance field in the same way that cathode tubes might project a capacitance field. Your normal television tube consists of a cathode tube in which a flow of electrons go from the negative terminal to the positive terminal across a space of separation. And this, if you move your hand close to a television screen, you will find that the hairs on your hand will start to stand up. That the screen is putting out a capacitance field because electrons are flowing across the space of separation. That is putting on a capacitance field that maybe is 4 to 5 inches at most of observable space. We were finding that the beta discharges were also crossing a space of separation, entering into the positive terminal in the same way that the television tube works, but it was putting out a capacitance field that was many times that experienced with a television set. For example, in order to protect our equipment from the 25,000 voltage field that we were using, we had to set the recording computer as far away from the experiment as we could. We had it at least 4 feet away. Yet, when this experiment was being run, this generated a sparking capacitance field in the plastic casing of this computer, such that a spark was jumped across a space of separation about a quarter of an inch or more into my finger.